Hello everyone. In this video, we're going to be proving this theorem that you see right at the top here, which is telling us that the limit of sequences in R they're unique, right? So they are, unique. And remember that we have the idea that of a limit here of a sequence is that is stated right here, right? Which means that for all epsilon greater than 0, there exists some n such that when all the terms are past that point, the distance from the limit is less than epsilon. This works for any epsilon. Not very hard to prove, but kind of a fun use of the definition. So we kind of go how these uniqueness proofs usually work, which is to say, try to say, like, well, let's say we have two limits of the sequence, right? So suppose an, which is this sequence in R, converges, and also further suppose that we have that an converges to A, and also an converges to B. We show A equals B. Okay. Well, let's see how this could be, right? So if an converges to A, then this tells us that for all epsilon greater than 0, there exists an n, call it an A maybe, an A in n, such that a n minus A is less than epsilon for all n greater than or equal to na. And nb, an converges to B. This tells us a similar thing, right? So maybe, that's fine. So for all epsilon greater than 0, there exists some nb in n such that an minus A is less than epsilon for all n greater than or equal to nb. Okay, so now let's consider A minus B, right? The difference between A and B. Oh, I made a mistake here. That should be a B, right? That should be a B there. Okay, well, we know that it's kind of what we're considering here. From this bound, how should I call it, right? I'll call this right here maybe star A. I'll call this star B, right? So if we take star A, we know that means that that an minus A is between negative epsilon and epsilon, and an minus B is between negative epsilon and epsilon, right? So that's from star A and star B. And we can just kind of take the right-hand sides of these facts and subtract them, right? So well, what we can do first really is flip one of them. So let's say maybe I take this bottom inequality and I turn that. So maybe I just give a little note here, right? We take star B, multiply everything by -1, so we get epsilon, that's the row backwards, epsilon B minus an negative epsilon. I mean, of course that doesn't change, right? So it's pretty much the same thing. And so anyways, what do we know? We know that an minus A is less than epsilon. And we also know that B minus an is less than epsilon. So that's from this side right here. So we can now add these inequalities together, right? And we get that an minus A plus B minus an is less than epsilon, less than 2 epsilon, right? And so we clearly get that B minus A is less than 2 epsilon. And right, and the point is that this is for some choice of epsilon, right? So I would choose some epsilon, whatever epsilon I want, then there is a way to find NA and NB that make this true. And so we maybe just take the max of them, right? So we could just say maybe, I'll write that here, right? Fix epsilon equals, maybe actually, well, it's going to be epsilon over 2, but whatever, fix epsilon. Then there exists the NAs and NBs in N that we want, and pick N to be the max of the two, right? So the later one of both of them, whatever it is. And that's possible to take. And so with that in mind, then we can have all these inequalities. And so, yeah, we add these two together. And so we get this. And so now we have that B minus A is less than 2 epsilon for all epsilon greater than 0, right? For all epsilon greater than 0. Now, actually, we probably want to modify this a bit because we don't want to have, it doesn't really matter, but we don't want to have 2 epsilon. We'd like this to be less than epsilon because we're going to use a fact here, which is to say that if B minus A is less than epsilon for all epsilon greater than 0, then this implies that A equals B, right? And we can maybe have that as a claim here, which I can prove if you want, but it's probably a good exercise. But anyways, that's an important fact. And so we just want an epsilon there. Doesn't really matter. 2 epsilon. Epsilon's any small number. So if I want 2 epsilon to be smaller, then I just divide this by 2, which is essentially what we're going to do, right? So if I just modify this a bit, if I want for all epsilon over 2 greater than 0, then we know that all of these should be epsilons over 2's. And so we get epsilon over 2, epsilon over 2. 2 epsilon over 2 is just epsilon, right? And there we go. So that's maybe the fix that we might want to have there, and that would work. Yeah, okay. Well, so maybe fix epsilon over 2 or something like that. And and we essentially have it, right? So that's essentially the fact that we have. So therefore, we can conclude that A equals B. And we are done with the uniqueness. We just sketch this idea, right? So the idea here is that, by contradiction, we could say, well, if this is true and they're not equal, well, they contradict something because we could make a epsilon small enough to be smaller than the difference between them, right? Because if this is some non-negative number, right, or positive number, right, non-zero number, then there's some epsilon we can choose here, right? That makes them bigger or smaller. So we'd get a contradiction. Anyways, the main proof is this fact, right? So we can kind of combine the facts that we have about the two sequences in a smart way, so that when we add these two inequalities together, we get the result that we want. Okay, that's all.